So I'm
Yeah,
Skylar Tibbits. I'm faculty at MIT. I run a research lab called the Self-Assembly Lab. I have a background in architecture, and then I did design computation and computer science. And outside of MIT, I run the 3D Printing Additive Manufacturing Journal. So welcome everyone to submit to us, and hopefully it's quite relevant to this audience. But the thing that excites me when I came in, I took over from Hod Lipson and added the plus sign. One hinting at, what's beyond 3D, like 4D printing or many others, but also just expanding it to all things additive. That it's not necessarily only about printing, but there's lots of additive fabrication processes, and so we're interested in all of those and expanding the field. As I said, I run a lab called the Self-Assembly Lab. And I'll try to explain some of the research that we do, but we look at our work sort of at three scales. Macro scale materials. We don't really invent new materials, but we combine materials to create new composites and new material properties. We develop fabrication processes and we work on larger scale construction systems. But the ethos of the lab, as sort of the name suggests, we're interested in self-assembly, self-organization, reconfiguration, shape change, those kind of principles. And all of it is about how do we build smarter things and how do we build in a smarter way. Coming from my background in architecture, I'm really interested in challenging the ways that we fabricate, the ways that we construct. And a lot of this started with a question or a curiosity as to why in the human world, human built world, we build from the top down, but in almost every other scale, whether that's small scale structures, think of biology and chemistry and nanoscale phenomenon, or think of large scale like planetary or geology. Everything happens from the bottom up. Everything is designed and fabricated through self-organization or self-assembly. The environment provides energy, materials interact with one another, they connect or disconnect, and therefore both design and functionality emerge. And so a lot of our research is like trying to challenge that process. I'm going to talk mostly about our materials and then go a little bit into the fabrication and construction system. So we call the materials our programmable materials, the idea that we want to have physical materials that we can program to change shape, change property, act as sensors, actuators, and we try to do that all without electromechanical means. So we try to do that through material properties and fabrication. And these are sort of the ingredients that we look at. We look at the material properties fairly closely, and we try to tune those properties towards the activation energy. So if you have wood, that can be activated by moisture. If you have metals or polymers or, different materials, that might be temperature, it might be pressure, it might be sunlight, different kinds of activation energies. But the real key is that you design the geometry, and, that can happen through printing, but it can happen through many other fabrication processes. And so we design that geometry to encode the information directly into the materials. And you can think about wood grain, or you can think about, the architecture of a textile, or the layup of a composite, and those encode information like zeros and ones or ACTG. All that information is embedded in the material through geometry. And by linking up the materials and geometry and the energy, that leads to some kind of sense and actuation, some type of transformation. And most of our work is about physical transformations, not necessarily optical or aesthetic or color, although that, obviously can also tie in, but mostly it's about things that either assemble themselves or transform themselves. And as the name of this conference suggests, we have done 4D printing in the past and introduced this topic in roughly 2013, 2012, somewhere around there. And the idea originally was to take 3D printing and add the element of time. And, I probably don't need to explain that principle to many people here. But a lot of this came out of, I was under a DARPA grant for programmable matter. And I was working at Neil Gershenfeld's lab as a graduate student before becoming faculty. And at that time, over a decade ago, I guess it's almost like 15 years ago, programmable matter meant robots. So we would program matter at the smallest of scales and largest of scales with robots, build everything out of robots. And this is sort of like the Big Hero 6 kind of vision, or, Terminator vision. And, we did that. We did small scale. We had microbots, and then I was building a macrobot and a decibot. We built large scale reconfigurable robots. But I sort of started to question that, mostly because of my architecture background. You don't really want to build everything out of robots. If you want to build a building, every brick can't be a robot. It's too energy intensive, too expensive, too costly, too much failure prone, hard to assemble, that kind of stuff. So we want the functionality, the intelligence, the sensing and actuation, perhaps, of robotics and the programmability, but we don't want the robot part of the robot. And so that's where the 4D printing work came out of. And actually, there's a funny backstory that's maybe interesting. This group that I was at a coffee shop, and there was a person standing next to me in the line that had a Stratasys Objet shirt on. And that's how this whole project started. I was like, do you work for the 3D printing company, Stratasys, like Objet? And then I just threw it out there and said, like, why can't we print robots? Why can't we use multi-material printing to make things that are active? Like, imagine you print something and it walks off the machine. And that led to this collaboration of 4D printing. And we figured out how to do that originally through two different materials. The material in the joints is a hydrogel that swells with water, and then the black was just a rigid plastic that provides all the structure and geometry and precision so that we could go from one shape to another. And over a number of years, we did a lot of demonstrations, like a line that folds into a cube, or a line that folds into the letters MIT, or a surface that folds into a truncated octahedron, or a flat sheet that has curved crease origami. And we did some of this with Eric and Marty Domain. We're like origami masters. We did a expanding and contracting one. So this is a flat sheet that produces doubly curved surfaces without any forming. And in textiles or automotive or architecture, this is a whole problem. How do you get flat sheets to go into curvature? And we showed that expansion and contraction. But if you look at all those, they're studying different mechanisms like folding or curling, or the flat sheet one, or joints, 1D, 2D, 3D. This was a 50-foot structure we printed and dipped in the Olympic swimming pool that was printing a protein, macro scale protein. So we did a lot of different experiments. Each one was to kind of take on the previous one. Okay, we could do 1D to 2D. Well, what if we did 1D to 3D? Or what if we, in the beginning, we could only fold to 90 degrees, but then we figured out how to fold to any angle, which was one of this one. Or what if we did a really large one? What if we did surfaces? We were just experimenting with what was possible. But after presenting that, and over the past 13 years or so, the same question keeps coming up. A lot of people are like, this is great, 4D printing is amazing, but we don't care about 3D printing. We don't care about plastics. How do we do this with real materials? How do we do this with real manufacturing processes? How do we do it in shoes, cars, planes, buildings, medical, you name it, many applications. So that has become the focus of the lab, that it's not just about printing, actually. Printing was a way we could do it in the beginning, but realistically, it's about embedding information and agency in our materials in order to get smarter, more active sensing, actuation. We want more intelligence, more agency embedded in our products, our everyday world, our environment. So that can be clothing, building, shoes, cars, planes, trains, you name it. So over many years, we've collaborated with a lot of people, academics and industry, developed a lot of work around this, like printed wood that morphs based on moisture, or carbon fiber that transforms based on temperature change. Or we had a page in one of our books that was active based on light. And we've done a lot of different things, from printing to lamination. These ones are all films that can be laminated to anything from like leather and ripstop to textiles to, used on their own. We've done a shading system with Google for buildings. Then we slitted them and recombined them into auxetic structures, and eventually then started to think about them on the body. And we've worked on a lot of different industry applications of this, like many different materials, many different manufacturing processes. And so the vision has become much bigger than just printing and just plastics, but that really you could do this with almost any material. And there are certain fabrication processes, like textiles, for example, we can embed this, and there's many others. You can do this with lamination or injection or whatever. I'm going to show you a bunch of textiles related projects because that has become a big thing in our lab, but there's lots of other ones. One of the most simple ways that we started thinking about doing this in the beginning, without making the textile from scratch, we take a stretch textile, so like a Lycra type textile, we stretch it around a plate, and then we print in 2D onto that, and we print just a passive flexible polymer, so nothing active about it. It's not swelling or shrinking or anything. but the stretch is what embodies the transformation. So the geometry tells it, go from a circle to a hyperbolic paraboloid, and the stretch of the textile, you can either do that uniformly or directionally. That gives you the activation energy to transform. So we've done a lot of different projects around that stretch textile, and that obviously has expanded a lot beyond our lab as well. But one of the early interesting demonstrations, we got invited to do this exhibit in London. We printed a flat sheet with this pattern, and then when you cut it out, it jumps into the full shape of the shoe. And we were interested in challenging the fabrication and manufacturing of shoes. I've seen a lot of 3D printed shoes, but realistically, they're 3D printed midsoles slapped onto a typical upper with lots of gluing, stitching, forming. Shoes have hundreds of parts, almost all manually formed. There's some 3D printed of full shoes, but then you're walking around with big plastic shoes around. So, how do we get a nice textile surface that can form itself? And so that was one of those kind of early demonstrations, and that has translated to a lot of footwear projects over the years. But then we started thinking about, well, what if we make the textile from scratch? There's a boom in industrial knitting. So we have a large scale flatbed industrial knitting machine. And it's very much like a printer. So we can, instead of droplet by droplet, we can change the material stitch by stitch. We can use many different materials. We can change the material properties or the combination of those materials. And then we can have different knitted architectures that then transform how the material behaves or how the textile behaves. The first one was based on moisture, and the color change was pH sensing. This one's based on temperature. So in a way, industrial knitting is everything we've been dreaming of for printing, but even more because it's truly scalable. So the same machine that we have is in thousands of manufacturing facilities around the world, and you can translate the code and build, full-scale final products directly, which is what printing has always dreamed of doing. But in this case, we can do it with textiles and modulate the material properties. And you can go from the smallest of scale, like we make our own fibers and filaments. Sometimes we use off-the-shelf yarns. Then you can go to, fibers, filaments, to twisting into different yarns. Then you can go up to what is the actual stitch configuration and what is the cross-section and three-dimensional surface of the textile. And then you can go all the way into zones. This one was focused on tailoring. So how do we develop textiles that can be made at a mass standardized? So just same, standard product. So it's not customized, but then we can tailor it by activating it. So we make one sweater in this case, we can then activate it based on the dimensions of the body and tailor the garment to the person. And this gets into a much larger discussion about mass customization that we can talk about later, but 3D printing has been talking about that for a long time and hasn't really overcome the logistics challenges. Yes, it's technically possible to mass customize your product, but how do you get that one-off product from some random factory around the world to this customer? And how do you get the data there and back? And how do you ensure quality control? There's a lot of issues with that. And textiles have even more issues. So instead of trying to do mass customization and instead of doing just standardization, but human tailored, which almost never no one wants to do, what if you can standardize the production, but you can make it morph to tailor it to the individual? And so that was that project, and we've done a series of others. This one was reversible temperature change. So the tailoring is only single direction. This project was about how do we get active textiles that reversibly morph in order to control your comfort in different temperature ranges. So it's super hot outside and you go in an air-conditioned room, or it's super cold outside and you go inside and it's hot. So we developed our own custom fiber extrusions. It's two different materials, different colors and cross sections, material properties. So very much like the 4D printing, that's extruded. It's then spun into yarns. We use twisting as a way to amplify it. And then we knit different architectures to get different behaviors. And we can get thickness change and bulking, or we can get porosity change, or we can get curling. Like you saw that one little gray swatch. We can get textiles that physically morph, and this is reversible. So we get a drastic temperature swing when you go inside to outside, depending on the time of year. And then the textile can expand or contract. And then this shows the zone. So we can then knit the entire garment in 3 dimensions. We can also knit with different cross-sectional volumes, and the different zones can have different functions. So you can have zones that open and close pores, or you can have flaps that open and close for ventilation. You can have thickness change. So we have an insulation project right now with a big outdoor outerwear company, and we have a swimsuit project on adaptive fit right now. We've done some footwear projects. So a lot of different textiles work. At the beginning of the pandemic, we were working a lot with Ministry of Supplies, MIT spin out clothing company, and they switched all their manufacturing to masks. So we helped a lot in that front. But then we started to translate some of the active research into masks. And one of our PhD students, Lavender Testmer, led this project where we make a standardized mask. We take 6 measurements from anyone's face, and then we can robotically morph the mask to give you a perfect fit. So we don't have to have perfect production based on everyone's face. We can have a standard production, but we can still tailor it to the individual user. And then more recently, we collaborated with David Newman and Hugh Herr and a few others on campus on developing a spacesuit prototype. We developed a sleeve. And it's really trying to challenge the like bulkiness of traditional spacesuits. There's something like 7 different layers, and they have pneumatics and air pressure and sensing and all these different functions and different material configurations. So our proposal is that we would do a mechanical counter pressure suit, which is a whole different type of suit that doesn't use air pressure. And we would knit the entire suit with all the functionality embedded into the knitted structure. So we have all of these different layers knitted into the structure of it. On the inside, there's sensing layers. On the outside, there's radiation shielding layers. There's padding and kind of cushion zones. And then maybe most relevant to our group, what we were trying to show is that we can get tunable compression across a non-uniform surface like the body. So, if you think about yoga pants, the amount of compression you need to be safe in the space environment is like 20 pairs of yoga pants at the same time. So it's a lot of compression. But yoga pants or any like traditional stretch textile is uniform, and our bodies are not uniform and they're dynamic. We move. So how do you get uniform compression on a non-uniform dynamic body? And so that's the way that we can tune that is through the knitted structure. We have easy donning and doffing and sensing and all these other things. So it's a very like highly functional multi-system integrated thing directly from the knitting machine. And a lot of that was built on David Newman, who's the head of the Media Lab, and her whole research is on spacesuits. I'll then get into fabrication systems. So, as I'm talking about, we develop a lot of these kind of material composites, but they go hand in hand with fabrication systems. Obviously, in the beginning with the 4D printing work, we were using the Stratasys Connex machines, and that's great, but they're sort of black box. And we see the 3D printing world as like you have really high-end expensive machines that are very precise but very expensive, and you can't really do a lot of research on them, and they're challenging. They break all the time. You can't manipulate the materials. And then you have very low-end, low-cost machines that you can do a lot of things with. You can build, you can break, you can test, you can mess with, but usually don't have great resolution. They don't have great quality. They break all the time, etc. So we are trying to develop things that are in the middle, that they're highly customized. They're useful for researchers, useful for anyone that wants to be able to tune things, but they can really do what we need them to do, and they're not black box. And so eventually we developed our own printing process called rapid liquid printing. And we print inside of a tank of gel. So the gel eliminates gravity. We don't have to print support materials. We don't have to print layer by layer, although you can print spatially. We can vary the thickness of the print by changing the speed or the pressure on the fly. So we can have dynamic line weights, and everything's liquid. These are typically we're printing with 2-part chemical cure materials. So polyurethane, silicones, foams, rubbers. We can do some acrylics. We can do some UV cured resins, etc. But what's super cool is we can print very, very soft, like 1000% elongation, highly elastic materials like silicone, rubber, and foams. We can also print rigid things. But so you get really nice, high quality industrial materials. There's no like quote unquote 3D printed material, which is one of the limitations of traditional 3D printing. These are all industrially standard materials. So they can be food safe, they can be, medical grade, or all the same properties that industry would want. And we can print those really high quality material properties. We print very fast. So usually it's tens of minutes, like less than an hour. It's something like 20 minutes to print a prosthetic device, or, maybe less than that, 10 minutes to print a insole for a shoe. We print like bags and all sorts of other things. This was a seat prototype with BMW to develop an adaptive cushion. So think about replacing foams with this kind of cushion that would expand or contract to morph around your body, provide crash protection, massage features, all sorts of multifunctional things. But we've done many different projects around the liquid printing. We've done like home goods and lamps and toothbrush holders to shoes to medical devices. And then more recently, we spun this out as a company. They're based out of Boston. And so they do a lot of this commercially now, and we don't do as much on the research side with that. But research-wise, we then started to go into high temperature metals. So one of the downsides of the previous one is that you couldn't print with anything over the boiling temperature of water. So there's a lot of benefits, but what if we want to do high temperature things? So we translated this into liquid metal printing. So we print at roughly 700 C. We print molten aluminum into a powder bath. The powder is polishing media, so it's really, really fine. It can receive the high temperatures. We print in less than a minute. So we have a 2-foot by 4-foot bed, so fairly large scale bed. We print less than a minute, molten aluminum. So it's almost like sand casting, but it's direct writing of sand casted structures. Benefits here are the same kind of thing, very, very fast, almost the fastest process you can imagine for printing. Fairly large, meter scale objects, and then high quality, true industrial material. So same quality of printed part as you would get from a sand casted part in aluminum. So we've done a lot of research on this, and it's still active area. We've done some furniture projects and some automotive applications, et cetera. I think I will skip over that, and I'll talk to you about the last category research on the self-assembly work. And a lot of this started with true self-assembly, but at a macro scale, like underwater, in the air, how do particles come together? How do we, in this case, it was like, how do we have a component that is unique and it only has one place in a larger structure, so it can make things like chairs. We did weather balloons filled with helium that had Velcro nodes, and they move around inside of a courtyard, and they build cubic lattice structures, so you can build things like beams and space frames, etc. We did big things, small things, standardized, uniform, non-uniform structures, periodic, non-periodic, all sorts of different attachment mechanisms, different energies. But a lot of this research was really like quote unquote basic research, at least from the architecture world. Like, why does it work? What are the principles? How do we scale it? How do we change the properties? It was very far futures. It wasn't very applied. But more recently, over the past several years, we've been working on a very applied project in the Maldives. This is probably far outside of the scope of the conference, but I thought maybe interesting just in like the largest of scales you can imagine. So we're trying to tackle the challenges with sea level rise and storm inundation or erosion. And there's really only two things, like fight the forces of nature, build barriers and walls, or dredging. So pump sand from the deep ocean to rebuild beaches or to make new islands, for example. But dredging is super bad for the environment, destroys all the coral. It's really nasty, heavy, expensive. It doesn't solve the problem as well. So all the beaches erode the next year. So these two solutions are the only thing people do, and they don't really do anything, don't work. So we have started to study how do we do this in a different way. And so they can dredge an island in roughly a month. So they can make a new island in the Maldives or many places in the Middle East or around the world. They can do that in about a month. But at the same time that they did that, 3 different sandbars built themselves. And so we became really fascinated in how do islands grow? How do sandbars build themselves? How does the self-assembly, self-organization process work? And can we tap into that? Could we make islands grow themselves where we needed them? And so we started to study, why does this happen? How do sandbars and islands form? It's very complicated. We don't necessarily know all the reasons, but realistically, we boiled it down to the force of the water. So think waves, currents, tides. So that has a force, and the geometry or the bathymetry underwater. And the relationship between those two causes sand to accumulate, erode or do something. So the relationship of the force of the ocean and the bathymetry then can be a tool. So we have done a lot of work over the years in this, from lab scale to field scale. But what we're proposing is to work with the forces of nature to build rather than destroy. So in our lab, we set up wave tanks, and we have a recirculating flume that we can do current flow, and we can raise and lower for tides. In this case, we pump waves, we place a very specific geometry underwater, and then we study how the sand accumulates based on that geometry. We've done this for many different kinds of experiments, basically all trying to test what is the influence of geometry underwater and the force of that, the movement of that water, and how does sand accumulate or not. And that's sort of like a small scale model for the field. This one is more like a satellite view. So imagine you're a satellite looking down. We have 8 different pumps. We can turn them on and off, which is basically like changing the weather. And then we study how the sand self-organizes based on the force of the flow of water. And then we can place obstructions in there and study how the sand moves around those obstructions. So this is like every one of those might be a sandbar, or might be an island. And now we've translated that to some machine learning for satellite work, and we're trying to do a global monitoring system that can both monitor and predict how sand is moving through satellites. But most interestingly, we then translate this to the full scale, meter scale in the Maldives. So we did a first one where it was like almost identical to what you saw in that tank. It's basically this ramp-like geometry, and we had a series of bladders. Then we did a much larger one, which is a 20-meter structure. Same thing, we place it underwater. It's completely passive, so there's no like, actuation. It's not motorized, not pumping or anything. It's just a specific geometry, and the ocean provides all the energy. We placed that, and within 4 months, we got a 0.5 meter of sand. And so you can see on the right-hand side is after 4 months, there's a 0.5 meter of new sand, and it's just passive. But then over the past 3 years, we've now gotten 2 meters of sand. So the sand is all the way to the top of the structure. The structure was 2 meters tall. So we've gotten 2 meters of new sand accumulation just by having the right geometry and the right orientation. And we've studied this in different structures. This was a low cost, quickly deployable one. So we can do 30-meter structure in roughly an hour. We deploy these. This sort of amphibious excavator just goes out and we deploy them. In this case, it's off a beach. And then we've started to look at how vegetation can create stabilization. So what's cool about this is the vegetation can grow. It's, obviously a natural system, and it can trap more sediment, but it then can also stabilize the sediment that does accumulate. And so the first version of this, we did a floating series of gardens. So we deployed these floats, we had moorings, and then we have these little like garden modules that you'll see we place in there. And the garden modules had native plants, so mangroves and screw pine and various other plants that went in there. And so these are floating, hovering above the bladder. And then the idea is that they will grow down, grow into the bladder, and then sand will be trapped more, and it'll stabilize the sand and hopefully create sort of a recursive system. This is one of the bladders. And then most recently, we started to think about how do we use a synthetic version of vegetation to have networks, like a mangrove network. But problem is mangroves are very, very slow, take a long time to grow, relatively fragile. So how do we create a network system very quickly so we can deploy nets, and then those nets can trap sand? And so we're looking at different densities of these fields. And one of our collaborators, Heidi Knepp, her whole research at MIT is about fields and densities of fields and how they change the velocity and sand accumulation. So anyway, that's a sort of like crazy far out there research project that we're doing, but connects back to this ethos. And again, we're trying to develop a fairly low cost, easy to deploy system that's completely passive, but is in tune with the forces of nature to try to build and naturally accumulate sand. But all of this research is still going back to those same questions. How do we build in a smarter way, and how do we build smarter things? Most of the time, if we think about smart systems, like think of a smart home, we automatically think of Nest thermostats, or think about like smart shoes. Nike had Back to the Future self-lacing shoes. They put a bunch of motors and sensors in it. Think about smart cars, smart whatever it is, smart clothing. We're trying to put motors, sensors in our clothing. And I think we should go a different direction. I don't think that the electromechanical solution of quote unquote smartness is the right direction. No one wants batteries in their clothes and their shoes and motors and their stuff. Everyone wants the intelligence and the sensing and the kind of human-like capabilities, but we don't want the electromechanical. It adds too much cost, too much failure, too much assembly, too much energy consumption, et cetera. So the real question is, how do we do this without the electromechanical functions? But you could say the most humble version of this is that robotics aren't going away. We'll have robotics everywhere in our lives, and we'll be more and more inundated with robotics. And maybe that's true. And there's great things about robots, especially in manufacturing. They're very precise. They don't get tired. They can be reprogrammed infinitely, et cetera. But even if that's true, we still want to have smarter materials that collaborate with robots and collaborate with humans in the environment. And the great thing about materials is that they are based on physics and they respond to the environment. They can be tuned into sensing different signals that humans or robots can't necessarily do. And they have material properties that can adapt. They can have information sensing and actuation. Humans are creative and collaborative. And so we can have this really interesting dialogue. But I think the more ambitious one, and if we go all the way back to that DARPA program on programmable matter, like 15 years ago, almost every one of those researchers now has moved away from electromechanical systems into soft robotics, 4D printing, programmable materials, textiles, synthetic biology, granular jamming, all these soft material, physics-based robotics things. And that's because we've demonstrated collectively as a field information sensing and actuation, which are like the core fundamentals of robotics, can be embedded in materials with different fabrication processes. So the vision of our group is today we build smart robots and machines, and tomorrow we'll build smarter materials and environments.